March 1943, and Technical Sergeant Frank Kowalski is standing in the maintenance area at Bodney Airfield in England, staring at a Republic P-47 Thunderbolt that just limped back from a disastrous mission over occupied France. The cowling is peppered with flak damage, but that's not what has his attention. What bothers him is the combat report sitting on his toolbox. Pilot statement: couldn't gain altitude fast enough to engage. Lost 2 aircraft because we were still climbing when the 109s bounced us from above. It's the third report like this in 2 weeks. The P-47 Thunderbolt, that massive 7-ton fighter that everyone said would dominate the European skies, is getting caught with its pants down. Not because it can't fly high. The turbo supercharger can push it to 40,000 feet, higher than anything the Luftwaffe flies. The problem is getting there. While German fighters climb at 3,000 feet per minute, these Thunderbolts are wheezing their way up at barely 2,000. By the time American pilots reach fighting altitude, the enemy has already positioned themselves, already owns the high ground, already holds every advantage. Kowalski has been turning wrenches since before the war. He worked in coal country Pennsylvania, keeping mining equipment alive with spit and prayer and an intuitive understanding of how machines actually work. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today, versus how engineers say they should work. He's seen the technical manuals for the P-47's Pratt & Whitney R2800 engine and its elaborate turbo supercharger system. Beautiful engineering, sophisticated beyond anything he'd worked on before the war, and according to every report crossing his desk, not performing where it mattered most. The Army Air Forces desperately needs the P-47 to work. By spring 1943, the 8th Air Force is bleeding. B-17 seconds going down over Germany in horrifying numbers because their fighter escorts can't climb fast enough to intercept Luftwaffe attacks. The P-47 was supposed to solve that problem. Instead, it's becoming another liability. Republic Aviation's engineers in Farmingdale insist the aircraft is performing to specifications. Test pilots at Wright Field confirm that climb rates match design parameters. Everyone in an engineering capacity is telling commanders that nothing is wrong. But Kowalski stands on the flight line every day, watching pilots come back frustrated, frightened, and sometimes not at all. He's learned something over 20 years of keeping machines running. Specifications don't mean a damn thing when the real world refuses to cooperate. And right now, the real world over Europe is proving that the P-47's climb rate is inadequate for the mission it's being asked to perform. The turbo supercharger system on the P-47 is legitimately revolutionary. Exhaust gases from the 18-cylinder R2800 engine flow rearward through heavy steel ducting to a General Electric turbine mounted in the tail. Those gases, screaming hot at 1700 degrees, spin the turbine at 21,000 revolutions per minute. That turbine drives a compressor that forces dense air into the engine, maintaining sea-level air pressure even at stratospheric altitudes. It's why the Thunderbolt can operate at 40,000 feet when German fighters are gasping at 35,000. But Kowalski has noticed something everyone else seems to have missed. The climb rate problem isn't consistent. Some P-47 seconds in the squadron climb noticeably better than others, even though they're supposedly identical. Same model, same engine, same turbo supercharger. He's started tracking tail numbers against pilot reports, and a pattern emerges. Aircraft that have been in service longer, that have accumulated more flight hours and more maintenance interventions, seem to perform better than factory-fresh replacements. That makes no sense according to conventional logic. New aircraft should outperform worn ones. But Kowalski suspects something is happening during field maintenance that accidentally improves performance. Mechanics making small adjustments, changing settings, maybe deviating slightly from technical orders without realizing they're doing something beneficial. He decides to investigate systematically, starting with the turbo supercharger control system. The turbo's boost pressure is regulated by a wastegate, essentially a valve that dumps excess exhaust overboard instead of through the turbine. The wastegate position is controlled by an oil pressure regulator that responds to manifold pressure. When the pilot advances the throttle, manifold pressure drops momentarily. The regulator senses this, and it closes the wastegate slightly, directing more exhaust through the turbine, spinning it faster, producing more boost. It's an elegant feedback loop designed to maintain consistent power output. The technical manual specifies exact oil pressure settings for the wastegate regulator. These settings represent Republic Aviation's engineers, determining the safe, reliable balance between performance and engine longevity. Conservative settings that ensure the turbo supercharger won't overspeed, won't overboost the engine, won't create conditions that might lead to catastrophic failure. Good engineering. Safe engineering. Engineering that prioritizes the machine over the mission. Kowalski pulls the maintenance logs for the squadron's best climbing P-47, tail number 230767. He compares every entry against two aircraft that pilots consistently complain about. The difference isn't dramatic. It's buried in routine notes. Different mechanics have adjusted the wastegate regulator oil pressure at different times, and aircraft 230767 has somehow accumulated adjustments that pushed the setting higher than standard specification. Not by much. Maybe 5 pounds per square inch higher than the book says. But that small difference is allowing the wastegate to close more aggressively under throttle input, sending more exhaust through the turbine sooner, spooling up the turbo supercharger faster, delivering boost pressure more rapidly. The result is an engine that responds like it's got a shot of adrenaline. When the pilot needs climb power, the turbo delivers it immediately, instead of lazily winding up over several seconds. Those seconds add up. Over a 10,000-foot climb, faster turbo response translates to reaching altitude 30 to 45 seconds sooner. In combat, that's the difference between being in position to attack and being in position to get killed. Kowalski does something that could end his career. He takes a P-47 scheduled for routine maintenance and intentionally adjusts the wastegate regulator oil pressure beyond specification. Not recklessly beyond. He's not trying to blow up an engine, but measurably beyond what the technical manual allows. He documents everything in a personal notebook, not in official maintenance logs, because what he's doing is technically unauthorized modification of critical flight systems. The test pilot is a lieutenant named Jack Morrison, who's already been shot down once and has nothing but contempt for caution. Kowalski briefs him quietly. The aircraft might respond differently to throttle inputs, might climb better, might also do absolutely nothing. Morrison shrugs and takes it up. At 5,000 feet, Morrison advances the throttle to climb power and feels something he hasn't felt in a P-47 before. Immediate response. The engine doesn't hesitate. The turbo doesn't lag. Manifold pressure jumps instantly, and the Thunderbolt's nose lifts like it's been kicked from behind. At 10,000 feet, Morrison is grinning inside his oxygen mask. The rate of climb indicator is showing 2,400 feet per minute, 300 feet per minute better than any P-47 he's flown. At 15,000, still pulling strong. At 20,000, where most Thunderbolts start feeling heavy and sluggish, this one is still clawing upward with authority. Morrison pushes it to 30,000 feet, and the climb rate has only dropped to 1,800 feet per minute. That's extraordinary. That's competitive with German fighters. That's what the P-47 should have been doing all along. When Morrison lands, he finds Kowalski immediately. His exact words are preserved in Kowalski's personal notes. Whatever you did, do it to every aircraft in this squadron. Now. Tonight. I don't care if it's legal. Kowalski has a decision to make. What he's discovered works. Demonstrably, measurably works. But it's outside approved procedures. If something goes wrong, if an engine fails because of his modification, he'll face court-martial. If he does nothing, and pilots keep dying because their fighters can't climb fast enough, he'll have to live with that instead. He chooses the wrench over the manual. Over the next week, during routine maintenance shifts, Kowalski adjusts the wastegate regulator settings on every P-47 inches the squadron. He's careful. He doesn't push the settings into dangerous territory. He finds a sweet spot, 17 to 20 pounds per square inch higher than specification, that delivers dramatically improved throttle response without exceeding safe manifold pressure limits. He trains 2 other mechanics on exactly what he's doing and why, building a small conspiracy of wrench turners who understand that combat performance trumps engineering caution. The pilots notice immediately. Within 2 weeks, mission reports from the squadron start reading differently. Achieved intercept altitude ahead of bomber stream. Successfully climbed to engage enemy fighters. No losses to altitude disadvantage. Squadron Commander Lieutenant Colonel James Kasler knows something has changed, but he's smart enough not to ask too many questions. His pilots are coming home. His unit's effectiveness ratings are climbing. Whatever is happening, in the maintenance area, he wants it to continue happening. But word spreads the way it always does in military units. Pilots talk to other pilots. Mechanics compare notes. By May 1943, modified P-47 seconds are showing up across multiple squadrons at Bodney and neighbouring airfields. The modifications are happening quietly, off the books, spread through informal networks of senior enlisted men who trust each other more than they trust engineering manuals. It's a grassroots revolution in aircraft performance, and it's completely invisible to the official chain of command. Then someone gets noticed by someone who can't be ignored. Major General William Kepner, commander of 8th Fighter Command, is visiting Bodney Airfield in late May 1943 for a morale tour. He's scheduled to meet with squadron commanders, observe maintenance operations, and generally be seen by the troops. During the visit, he watches a flight of 4 P-47 seconds scramble on an intercept mission. The Thunderbolts claw into the sky with a climb rate that makes Kepner do a double take. He's flown P-47 seconds himself. He knows what their climb performance should look like. These aircraft are climbing like they've lost 2,000 pounds of weight. Kepner corners Lieutenant Colonel Kasler and asks a direct question. What's different about your aircraft? Kasler, who has carefully maintained plausible deniability about the modifications, responds honestly that his maintenance crews are exceptional and his aircraft are in optimal condition. Kepner isn't stupid. He presses. What are your mechanics doing that other squadrons aren't? Kasler realizes he can't deflect further and makes a judgment call. He brings Kepner to the maintenance area and introduces him to Technical Sergeant Frank Kowalski. Kowalski expects to be relieved of duty, possibly arrested. Instead, Kepner listens to his explanation of the wastegate regulator adjustment with the focused intensity of a man who understands exactly what he's hearing. Kepner had been an engineering officer before transitioning to command. He knows turbo supercharger systems. He understands immediately that Kowalski has found a way to optimize transient response at the cost of theoretical safety margins that were probably excessive to begin with. Kepner asks one question. Has any aircraft experienced engine failure attributable to this modification? Kowalski shows him the maintenance logs. Over 300 flights on modified aircraft. 0 engine failures. 0 turbo supercharger malfunctions. The only thing that's changed is climb performance, and it's changed dramatically for the better. Kepner makes a decision that reveals why he's a general. He tells Kowalski to brief the modification procedure to maintenance officers from every P-47 squadron in 8th Fighter Command, not as an optional suggestion. As standard operating procedure, effective immediately. Within 6 weeks, modified P-47 seconds are operating across England. The transformation in combat effectiveness is immediate and measurable. In June 1943, the 56th Fighter Group flying modified Thunderbolts escorts B-17 seconds to Bremen. Luftwaffe Bf-109Gs attempt their standard tactic, climbing to 30,000 feet to dive through the bomber formation. But the P-47 seconds beat them to altitude, arriving at 32,000 feet with enough energy to engage aggressively. The German fighters find themselves looking up at American fighters for the first time in the European theatre. 3 Bf-109s go down in flames before the rest break off the attack. The psychological impact on Luftwaffe pilots is significant. They've spent months learning to exploit the P-47's sluggish climb rate, timing their attacks to hit bomber formations before escorts arrive at optimal altitude. Suddenly, that timing doesn't work anymore. American fighters are reaching intercept position faster, with more energy, positioned to dictate engagement terms. German intelligence reports from summer 1943, captured after the war, specifically mention American P-47 seconds, demonstrating improved high-altitude performance inconsistent with previous encounters. Back at Republic Aviation in Farmingdale, engineers are hearing reports from the field that their aircraft are somehow performing better than design specifications predict. This is puzzling and slightly embarrassing. They'd built what they believed was an optimized system. The discovery that a field modification improves performance suggests their optimization wasn't optimal. In July 1943, Republic sends a technical team to England to investigate exactly what these rogue mechanics have done to their carefully engineered fighters. The Republic engineers arrive with a mixture of professional curiosity and defensive pride. They examine modified P-47 seconds, run engine tests, monitor turbo supercharger behavior under various power settings. What they find forces them to confront uncomfortable truths about their own design philosophy. The wastegate regulator settings specified in technical manuals had been established through ground testing and conservative extrapolation. Republic's engineers had prioritized reliability and longevity, setting parameters that ensured the turbo supercharger system would survive extended service with minimal maintenance. Those settings worked fine for the steady-state conditions of test flights. They were inadequate for the dynamic demands of combat, where pilots need maximum performance instantly and don't particularly care if the engine needs replacement after 200 hours instead of 300. Kowalski's modification didn't compromise safety. It compromised conservatism, and there's a difference. The modified settings still kept manifold pressure within acceptable limits. They still prevented turbo overspeed. They just did it with faster response and less margin for error. The Republic engineering team's report, filed in August 1943, acknowledged that field modifications had identified optimization opportunities not apparent during development testing. The language was carefully diplomatic, avoiding admission that enlisted mechanics had out-engineered their graduate degree designers. But the conclusion was clear. The modified wastegate regulator settings should be incorporated into production aircraft, and retrofit kits should be developed for existing P-47 seconds. The P-47C5 production block, which started rolling off the line in September 1943, incorporated revised wastegate regulator settings based directly on Kowalski's field modification. Republic also redesigned the oil pressure regulator housing to make the adjustment more reliable and less sensitive to temperature variations. They added calibration marks that made it easier for maintenance crews to set optimal pressure without extensive testing. It was Kowalski's hack made official, refined, and productionized. By October 1943, the modification had spread beyond 8th Fighter Command. P-47 squadrons in the Mediterranean theater received technical bulletins describing the wastegate adjustment procedure. Pilots in the Pacific, where P-47 seconds were beginning to arrive, got aircraft with the modification already implemented. The ripple effect of one mechanic's refusal to accept inadequate climb performance had touched every theater where Thunderbolts operated. The tactical implications reshaped American fighter doctrine. Before the modification, P-47 squadrons had been assigned to medium-altitude escort, protecting bombers between 15,000 and 25,000 feet, while higher-climbing P-38 Lightnings covered higher altitudes. After the modification, P-47 seconds could compete for high-altitude superiority. Mission planners started using Thunderbolts in roles previously reserved for other aircraft, exploiting their heavy firepower and durability at altitudes, where climb performance had previously been prohibitive. Colonel Hubert Zemke, commanding officer of the 56th Fighter Group and one of the most tactically innovative leaders in 8th Fighter Command, developed new engagement protocols specifically for modified P-47 seconds. His directive to squadron leaders emphasized aggressive climbing on intercept vectors, using the improved climb rate to reach station above bomber formations earlier, maintaining energy advantage throughout engagements. Zemke's tactics became standard across P-47 units and contributed significantly to the Thunderbolt's eventual dominance over European skies. The modification's success validated something military institutions are often reluctant to admit. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Field experience can reveal optimization opportunities that controlled testing misses. Republic's engineers weren't incompetent. Their testing methodology wasn't flawed. They simply couldn't replicate in peacetime the exact conditions and demands of aerial combat. Kowalski could, because he was there, watching pilots struggle, hearing their complaints, seeing where the gap existed between design, intent, and operational reality. Statistics tell the story with brutal clarity. In the first quarter of 1943, before widespread modification, P-47 squadrons in 8 Fighter Command achieved an average climb to 30,000 feet in approximately 15 minutes. After modification, average climb time dropped to 11 minutes. That 4-minute improvement translated directly into tactical advantage. Fighters reaching altitude sooner meant more time on station, more opportunities to engage enemy aircraft, better protection for bomber formations. Loss rates reflected the change. In March through May 1943, P-47 squadrons lost an average of 4.2 aircraft per 100 sorties. In June through August, after modification became widespread, losses dropped to 2.8 per 100 sorties. Not all of that. Improvement came from climb performance, obviously. Pilot experience, better tactics, and Luftwaffe attrition all contributed. But after-action reports consistently credited faster climb capability as a significant factor in mission success. Individual pilot accounts provide texture to the statistics. Captain Walker Mahurin, who would end the war with 19 aerial victories, described the modification's impact in a letter home in July 1943. He wrote that the P-47 finally felt like it could compete on equal terms with German fighters, that he no longer felt like he was fighting uphill every mission. Lieutenant Colonel Francis Gabreski, another ace with 28 kills, told reporters after the war that the climb rate improvement gave American pilots the confidence to be aggressive, to take fights they might have avoided previously because they knew they could climb out of trouble if necessary. The modification's success created an uncomfortable question for Army, Air Force's leadership. How many other aircraft were operating with suboptimal settings because engineers had been too conservative? How much performance was being left on the table across the entire inventory because peacetime testing didn't capture wartime demands? In late 1943, the Air Technical Service Command established field evaluation teams specifically tasked with collecting performance feedback from operational squadrons and identifying potential modifications that could be implemented quickly without waiting for formal engineering review cycles. It was an institutional acknowledgement that innovation doesn't only flow from drawing boards to flight lines. Sometimes it flows the other way. Technical Sergeant Frank Kowalski rotated back to the United States in early 1944. He received a Bronze Star for meritorious service, citation carefully worded to avoid explicitly mentioning unauthorized modifications. The medal citation praised his technical expertise and dedication to maintaining combat readiness, bureaucratic language that translated to, "We can't officially approve what you did, but we're glad you did it." Kowalski never sought publicity. Interviews with veterans from his squadron in later years paint him as quiet, competent, and fundamentally uninterested in recognition. He'd seen a problem, fixed it with the tools and knowledge available, and moved on. That pragmatic approach characterized the best enlisted maintainers throughout the war. They weren't trying to revolutionize anything. They were trying to bring their pilots home alive, and if that meant bending rules or ignoring manuals, then that's what happened. The broader legacy of Kowalski's modification extends beyond World War II. Post-war analysis of aircraft performance optimization identified the P-47 wastegate adjustment as a case study in field-driven innovation. Military technical schools began teaching the incident as an example of how operational feedback should inform engineering decisions. The Air Force formalized processes for rapid implementation of field modifications, recognizing that combat environments reveal optimization opportunities that peacetime testing cannot predict. Modern aviation maintenance doctrine includes specific provisions for field adjustments to engine control parameters within defined safety limits. The philosophy acknowledges that engineers establish conservative baselines, but operational conditions may warrant different settings. That flexibility traces directly to lessons learned from mechanics like Kowalski, who understood that specifications are guidelines, not absolute laws, and that the ultimate measure of performance is mission success, not adherence to manuals. Republic Aviation incorporated the lessons into post-war designs. The P-47 Newtons, final variant of the Thunderbolt, featured extensively revised turbo supercharger controls, with field-adjustable parameters explicitly called out in technical documentation. Engineers had learned that maintenance crews needed flexibility to optimize performance for specific operational conditions. The days of one-size-fits-all factory settings were over. By war's end, over 15,000 P-47 Thunderbolts had been produced. The vast majority incorporated either factory-modified wastegate regulator settings or field modifications based on Kowalski's original work. The Thunderbolt compiled an impressive combat record, 3,552 air-to-air victories in Europe alone, kill-to-loss ratios consistently above 4-1. It became one of the most successful American fighters of the war, and part of that success stemmed from a Pennsylvania mechanic who looked at an inadequate climb rate and decided the technical manual wasn't the final word. The human cost of the modification delay is impossible to calculate precisely. How many pilots died in early 1943 because their P-47 seconds couldn't climb fast? Enough? How many bombers went down because escort fighters arrived at altitude too late? Those questions have no definitive answers, but the pattern in loss rates before and after widespread modification suggests the number wasn't trivial. Every week that passed between Kowalski's initial discovery and formal implementation represented missions flown with compromised capability, opportunities for the enemy to exploit American weaknesses. That delay wasn't due to malice or incompetence. It was the natural friction of military bureaucracy meeting wartime urgency. Official channels exist for good reasons. Unauthorized modifications can cause catastrophic failures. Testing and validation prevent problems from being implemented fleet-wide. But those processes take time, and in combat, time has a body count. The tension between safety and effectiveness, between proper procedure and immediate need, defines every military maintenance operation in every war. Kowalski's choice to bypass official channels saved lives. It also could have ended lives if his modification had proven dangerous. He got lucky that his mechanical intuition was correct, that the margins he eliminated were truly excessive, that Republic's engineers had been overly conservative rather than appropriately cautious. A different mechanic making a different modification with less understanding might have caused the exact failures Kowalski's critics feared. The fact that it worked doesn't entirely justify the risk, but it does explain why commanders looked the other way. In 1986, 43 years after his modification changed P-47 performance, Frank Kowalski was interviewed for an oral history project at the Air Force Museum. He was 72 years old, retired from a post-war career maintaining industrial equipment. The interviewer asked him if he'd been scared of the consequences when he first started adjusting wastegate regulators beyond specification. Kowalski's response was characteristically direct. "I was more scared of telling pilots there was nothing I could do while they kept dying. Fear of court-martial is abstract. Fear of failing the guys depending on you is immediate." That answer captures something essential about the relationship between combat operators and the maintainers who keep them flying. It's not about regulations or specifications or engineering theory. It's about trust. Pilots trust mechanics to give them aircraft that will perform when their lives depend on it. Mechanics trust pilots to use that performance to accomplish the mission and survive. Everything else, all the rules and procedures and technical manuals, exists to support that fundamental relationship. When the rules interfere with the relationship, people like Kowalski find ways to work around them. The P-47 Thunderbolt story is typically told as a triumph of American engineering. Alexander Kartveli's brilliant design. Pratt & Whitney's powerful R2800 engine. General Electric's revolutionary turbo supercharger. All of that is true and important, but it's incomplete. The P-47 became truly effective when field mechanics closed the gap between design potential and operational reality. The engineers gave it the capability to climb to 40,000 feet. Kowalski gave it the ability to get there fast enough to matter. Modern aircraft development includes operational evaluation phases, specifically designed to identify the kind of optimization opportunities Kowalski discovered through necessity. Test pilots fly pre-production aircraft in simulated combat conditions. Maintainers document performance characteristics under various operational scenarios. Engineering teams analyze feedback and implement modifications before full production begins. The process acknowledges that design validation requires real-world testing under realistic conditions, a lesson purchased with the lives of pilots who flew inadequately optimized aircraft in early combat. The P-47 wastegate modification represents a specific technical solution to a specific performance problem, but it also represents something broader about how military organizations adapt and learn. Formal processes and official channels provide structure and prevent chaos. Field innovation and informal networks provide flexibility and enable rapid response. Successful military institutions balance both, maintaining enough structure to prevent dangerous improvisation while allowing enough flexibility to capture beneficial innovation. That balance is difficult to achieve and easy to lose, but it's essential to combat effectiveness. Understanding why the wastegate modification worked requires diving deeper into the physics of turbo supercharger systems and the specific demands of high-altitude combat. The Pratt & Whitney R2800 double wasp engine in the P-47 was a masterpiece of American engineering. 18 cylinders arranged in 2 rows, each displacing 2,800 cubic inches total, producing over 2,000 horsepower at sea level. But that power output depended entirely on the engine's ability to ingest adequate air. At sea level, air pressure is 14.7 pounds per square inch. At 25,000 feet, it drops to 6.5 pounds per square inch. Feed an engine half as much air, and you get roughly half as much power. The turbo supercharger solved this problem by using exhaust energy to compress incoming air back to sea level density. But the system's effectiveness depended on how quickly it could respond to changing demands. When a pilot flying at 20,000 feet suddenly needs maximum climb power, he advances the throttle. The engine immediately tries to consume more fuel and air. If the turbo supercharger responds slowly, there's a lag period where the engine is fuel-rich but air-poor. The mixture burns incompletely, power output remains low, and the aircraft responds sluggishly. Republic Aviation's engineers had calibrated the wastegate regulator to respond gradually, ramping up boost pressure over several seconds. This protected against shock loading of the turbo supercharger bearings and prevented sudden pressure spikes that could damage engine components. It was conservative engineering based on the assumption that gradual power changes were safer than abrupt ones. That assumption worked fine for transport, aircraft, or bombers making steady climbs. It was catastrophically wrong for fighters that needed maximum power instantly. Kowalski's modification allowed the wastegate to close more aggressively when the pilot demanded power. The turbo supercharger spun up faster, boost pressure arrived sooner, and the engine delivered maximum power within 2 seconds instead of 5 or 6. Those few seconds might seem trivial, but they compounded throughout a climb. Every time the pilot adjusted power settings, every time he maneuvered and needed to recover energy, the modified aircraft responded, faster. Over a 15,000-foot climb, those accumulated seconds added up to arriving at altitude nearly a minute sooner with significantly more energy available for combat. The modification also improved combat maneuvering characteristics in ways that weren't immediately obvious. During high-altitude dogfights, pilots constantly varied throttle settings. Rolling into a turn, you reduce power slightly to tighten the turn radius. Rolling out, you advance power to maintain speed. The lag in turbo supercharger response meant that standard P-47 seconds were always slightly behind the pilot's intentions. By the time boost pressure caught up with throttle position, the tactical situation had changed. Modified aircraft responded to throttle inputs almost instantly. Pilots reported that the aircraft felt more connected, more responsive, like the engine was reading their minds, rather than catching up to their hands. Lieutenant Robert Johnson, who flew both standard and modified P-47 seconds with the 56 Fighter Group, described it as the difference between driving a truck and driving a sports car. The truck eventually gets where you want it to go. The sports car goes there the moment you think about it. The psychological impact on pilots was as important as the performance improvement. Fighter combat is intensely stressful. Pilots are constantly monitoring threats, tracking friendlies, managing fuel and ammunition, and flying their aircraft at the edge of performance. Anything that reduces workload or increases confidence directly improves combat effectiveness. Modified P-47 seconds gave pilots confidence that their aircraft would respond when they needed it. That confidence translated into more aggressive tactics, better positioning, and ultimately more successful engagements. German pilots noticed the change before German intelligence services did. Luftwaffe, after-action reports from summer 1943 contain scattered references to American P-47 seconds performing differently than previous encounters suggested. One report from a Bf-109 pilot, shot down over France in July 1943, described attempting to extend vertically from American fighters and being shocked when the P-47 seconds followed him through a climbing turn. That should have left them behind. The pilot assumed he'd been fighting a different aircraft type until he was shown gun camera footage proving they were Thunderbolts. By August 1943, Luftwaffe tactical instructions began warning pilots that American P-47 seconds were more capable at altitude than earlier assessments indicated. The warnings didn't help much. German fighters were already stretched thin, facing overwhelming numerical odds and deteriorating fuel supplies. Even knowing that P-47 seconds could climb faster didn't give Luftwaffe pilots the resources to counter them effectively. The modification had arrived at exactly the right moment to exploit German weakness. The timing was crucial in another way. Spring and summer 1943 represented a critical period in the strategic bombing campaign over Europe. 8th Air Force was attempting to prove that daylight precision bombing could succeed without prohibitive losses. B-17 formations were striking deep into Germany, and loss rates were climbing toward unsustainable levels. The Luftwaffe was throwing everything it had at the bomber streams, knowing that if they could break American resolve, the entire strategic bombing campaign might collapse. P-47 escorts were supposed to protect those bombers, but their limited climb performance meant they often arrived at optimal altitude too late to prevent initial German attacks. Bomber crews watched escort fighters struggle to reach them, while German fighters dove through formations with impunity. Morale was suffering. Crews were completing tours, knowing that their survival depended more on luck than on fighter protection. The wastegate modification changed that calculation. By late summer 1943, bomber crews were reporting that fighter escorts were arriving at station earlier, maintaining position more effectively, and engaging German fighters more aggressively. Loss rates on missions with modified P-47 escorts dropped measurably compared to missions flown earlier in the year. That decline reinforced 8th Air Force Command's confidence that daylight bombing could succeed, which influenced the strategic direction of the entire air campaign over Europe. The modification's success created ripple effects throughout the American aviation industry. When Republic Aviation formally adopted the revised wastegate settings in production aircraft, other manufacturers took notice. Lockheed, still struggling with P-38 Lightning performance issues at altitude, accelerated their own intercooler modification program. Curtiss, producing P-40 Warhawks for secondary theaters, investigated whether similar turbo supercharger optimizations could improve their aircraft's performance. Even Bell Aircraft, working on the P-63 King Cobra, incorporated lessons about aggressive turbo control response into their design. Republic's P-47 was proving itself in combat, while Lockheed's P-38 continued to struggle with various technical problems. North American's P-51 Mustang was just entering service and would eventually prove superior in many respects, but in mid-1943, the P-47 was the most successful American fighter in Europe. Republic leveraged that success in negotiations with the Army Air Forces, securing continued production contracts and priority for resources. The modification also influenced training doctrine for new pilots. Flight schools began emphasizing aggressive throttle management and energy tactics that took advantage of improved turbo supercharger response. Instructors taught students to use rapid power changes during combat maneuvering, exploiting the P-47's ability to accelerate quickly in climbs. These techniques worked best with modified aircraft, which meant that by late 1943, the training curriculum assumed modifications that hadn't been official policy 6 months earlier. Maintenance training evolved as well. The Army Air Forces established technical schools specifically focused on turbo supercharger systems. Courses included modules on field optimization of wastegate regulators, teaching mechanics how to adjust settings for different operational conditions. The curriculum explicitly acknowledged that factory specifications represented baselines rather than optimal settings for all situations. Kowalski's unauthorized modification had become authorized doctrine. The political dimensions were subtle but important. The modification's success validated the judgment of field commanders who had quietly authorized it despite its unauthorized nature. General Kepner's decision to implement the modification across 8 Fighter Command without waiting for formal approval could have ended his career if it had failed. Instead, it enhanced his reputation as a leader willing to take calculated risks for operational advantage. That reputation helped him navigate later controversies and influenced how the Army Air Forces approached command selection for combat theaters. Republic Aviation's response to the modification also deserves examination. The company could have reacted defensively, arguing that field modifications voided warranties and created support problems. Instead, they embraced the feedback and incorporated it into production. That response reflected both good engineering practice and smart business strategy. By adopting field improvements quickly, Republic demonstrated responsiveness to customer needs. The Army Air Forces rewarded that responsiveness with continued contracts and support for future projects. The modification's long-term influence on aviation design philosophy extended beyond World War II into the jet age. Early jet engines faced similar challenges with throttle response. The centrifugal compressors used in first-generation jets like the P-80 Shooting Star had significant lag between throttle input and thrust output. Engineers designing these systems remembered the P-47 wastegate lessons and worked to minimize response lag, even if it required accepting narrower safety margins. Modern turbofan engines include sophisticated control systems that manage dozens of parameters, thousands of times per second, to optimize performance while protecting the engine. The full authority digital engine control, or FADEC systems, used in contemporary military and commercial aircraft, represent the ultimate evolution of the principles Kowalski applied manually. These systems constantly adjust fuel flow, variable inlet guide vanes, and bypass ratios to deliver exactly the thrust the pilot demands with minimum delay. The philosophy is identical. The engine should respond to the pilot's needs, instantly, and the control system should handle the complexity of making that happen safely. The human dimension of the modification story reveals tensions inherent in military hierarchies. Kowalski was an enlisted man making decisions that affected aircraft worth hundreds of thousands of dollars and pilots' lives. Officially, he had no authority to modify critical systems. Unofficially, he had the knowledge and proximity to the problem that officers and engineers lacked. The military's hierarchical structure struggles with this dynamic. Formal authority flows down from officers to enlisted ranks, but practical expertise often flows in the opposite direction. Smart officers recognize this and create space for enlisted expertise to influence decisions. Lieutenant Colonel Kassler did exactly that when he chose not to inquire too closely into what his mechanics were doing. He understood that maintaining plausible deniability while enabling innovation gave him the best of both worlds. If the modifications failed, he could claim ignorance. When they succeeded, he could claim credit for fostering an environment where excellence thrived. That kind of sophisticated leadership is rare and valuable. The contrast with other air forces is instructive. The Royal Air Force had a more rigid approach to aircraft modifications, requiring formal approval through engineering channels before implementing changes. This prevented dangerous field modifications, but also slowed the adoption of beneficial improvements. Soviet air forces operated at the opposite extreme, with field workshops routinely making extensive modifications to aircraft based on local needs and available materials. This enabled rapid adaptation but created maintenance and logistics nightmares as aircraft across different units became increasingly non-standard. The American approach, as exemplified by the P-47 wastegate modification, fell somewhere in the middle. Field modifications happened, sometimes without approval, but successful ones were quickly formalized and standardized. The system was messy and occasionally chaotic, but it allowed innovation to flow from the field to headquarters while maintaining enough structure to prevent complete chaos. That balance served American forces well throughout the war. The modification's impact on individual missions provides concrete examples of its value. On August 17, 1943, the 8th Air Force launched a massive raid against Schweinfurt and Regensburg, targeting ball-bearing factories critical to German war production. The mission required deep penetration into German airspace, beyond the range of conventional fighter escorts. P-47 seconds would escort the bombers as far as their fuel allowed, then turn back, leaving the B-17 seconds unprotected for the final leg. The 56th Fighter Group, flying modified P-47 seconds, escorted part of the bomber stream toward Regensburg. German fighters swarmed the formation at 28,000 feet, attempting to break up the bomber boxes before they reached the target. The P-47 seconds, climbing faster than previous escorts, arrived at optimal altitude with enough time to disrupt the German attacks. They engaged aggressively, using their altitude advantage to make diving passes that broke up German formations. The bombers still took losses, but the fighter escort limited the damage significantly. After-action reports from bomber crews specifically mentioned fighter escorts arriving earlier and maintaining better position than on previous deep penetration missions. Several bomber pilots credited the escort with preventing total disaster. Without the modified P-47 seconds' improved climb performance, the mission might have resulted in catastrophic losses that would have forced reconsideration of the entire daylight bombing strategy. Individual pilot experiences illustrate how the modification translated to survival. Second Lieutenant David Schilling of the 56th Fighter Group was escorting bombers over Holland in September 1943 when German fighters attacked from above. Standard procedure called for escorts to climb to meet the threat, but the altitude difference was significant. German fighters were at 32,000 feet while Schilling's flight was at 25,000. In a standard P-47, climbing 7,000 feet would have taken 4 to 5 minutes, far too long to intercept the Germans before they reached the bombers. Schilling's modified Thunderbolt climbed that altitude in just over 3 minutes, fast enough to position between the Germans and their targets. He engaged the lead element of Bf-109Gs, forcing them to break off their attack run. The bombers escaped damage, and Schilling was credited with saving multiple aircraft and crews. He later stated that in a standard P-47, he wouldn't have reached intercept position in time, and the Germans would have gotten through. The modification also affected loss rates among P-47 pilots themselves. Fighter combat over Europe was brutally attritional. Even successful pilots faced constant danger from enemy fighters, anti-aircraft fire, mechanical failures, and simple bad luck. Any advantage that improved survival odds mattered enormously. Modified P-47 seconds gave pilots better ability to control engagement parameters, choosing when to fight and when to disengage based on tactical advantage rather than aircraft limitations. Statistics from the 56th Fighter Group, one of the first units to adopt modified aircraft, show the impact. In the 4 months before widespread modification, April through July 1943, the group lost 19 pilots killed or missing in action. In the 4 months after, August through November, losses dropped to 11 pilots, despite flying significantly more missions and engaging in more combat. The reduction wasn't entirely due to the modification, but squadron commanders and pilots consistently credited improved climb performance as a major factor in their ability to survive and succeed. The modification's technical success also highlighted limitations in pre-war testing methodology. Republic Aviation had conducted extensive trials of the P-47 before delivering it to the Army Air Forces. Test pilots flew the aircraft through its performance envelope, documenting speed, range, climb rate, and handling characteristics. Engineers analyzed turbo supercharger performance under various conditions, validating that the system met design specifications. All of this testing occurred under controlled conditions with single aircraft flown by experienced test pilots. Combat operations presented entirely different demands. Multiple aircraft flying in formation, rapid throttle changes during combat maneuvering, sustained high-power operations at altitude, extended exposure to temperature extremes. These conditions revealed optimization opportunities that clean sheet testing couldn't identify. The lesson was clear. Peacetime testing validates design concepts, but operational testing reveals real performance. Post-war aircraft development incorporated this lesson by extending operational testing phases and involving combat-experienced pilots earlier in the design process. The Century Series fighters of the 1950s, the F-100, F-101, F-102, and their successors all underwent extensive operational evaluations before full production. Test units at Nellis Air Force Base and other facilities flew pre-production aircraft under simulated combat conditions, documenting performance characteristics and identifying optimization opportunities before problems reached fleet aircraft. The wastegate modification story also reveals how technical innovation depends on organizational culture. Republic Aviation's willingness to accept field feedback and quickly incorporate improvements reflected a corporate culture that valued performance over pride. Some companies and military organizations struggle with this. Admitting that field modifications improve on factory specifications feels like admitting failure. Leaders who prioritize appearing competent over being effective resist feedback that challenges their authority or expertise. Republic's leadership, particularly Chief Engineer Alexander Kartveli, demonstrated mature professionalism by embracing the modification. Kartveli reportedly told his engineering team that they should have identified the optimization opportunity themselves, but since they hadn't, they should learn from those who did. That attitude enabled Republic to maintain positive relationships with military customers and secure continued business. The modification's influence extended to other aircraft types through informal knowledge transfer. Mechanics who learned wastegate adjustment techniques on P-47 seconds carried that knowledge when they transferred to units flying different aircraft. The principles applied broadly. Any turbo supercharged engine could potentially benefit from optimized wastegate control. Mechanics working on B-17 seconds, B-24 seconds, and other heavy bombers started experimenting with similar adjustments, finding modest improvements in climb performance and engine reliability. These informal networks of technical knowledge represented one of the American military's significant advantages during World War II. Enlisted personnel rotated between units, sharing best practices and innovative techniques. Technical representatives from manufacturers visited operational units, collecting feedback and disseminating solutions. The result was a military force that learned and adapted continuously, incorporating lessons from combat into doctrine and practice with remarkable speed. The German military, by contrast, struggled with knowledge transfer across units. The Luftwaffe's maintenance doctrine was more centralized, with major modifications requiring approval from the Reich Aviation Ministry. Field units had less autonomy to implement improvements, and the devastation of German industry made it difficult to incorporate lessons even when they were identified. By 1943, The Luftwaffe was fighting desperately just to maintain existing aircraft, with no capacity for systematic improvement programs. This institutional difference compounded technical disparities. Even when German aircraft had superior performance in some areas, the Luftwaffe couldn't optimize their employment as effectively as American forces could. The P-47 wastegate modification was just one example of American ability to identify problems and implement solutions rapidly. That adaptability proved as important as raw industrial capacity in determining the air war's outcome. The modification's legacy in post-war aviation maintenance doctrine is substantial. The Air Force Technical Orders System, which governs aircraft maintenance procedures, includes specific provisions for field-level adjustments to engine control parameters. Maintenance manuals identify which settings can be adjusted within defined limits and provide guidance on optimization for different operational conditions. This flexibility acknowledges that factory specifications represent starting points, not final answers. Modern aircraft maintainers learn the wastegate modification story as part of their technical training. The lesson isn't that unauthorized modifications are acceptable. It's that understanding why systems are configured as they are enables intelligent optimization within safe parameters. Good maintainers don't just follow procedures. They understand the principles behind the procedures and can make informed judgments about when standard approaches need adaptation. The P-47 Thunderbolt flew its last combat mission in World War II on August 14, 1945, the day Japan surrendered. By then, over 15,000 Thunderbolts had been produced, and the vast majority incorporated optimized wastegate regulator settings descended from Kowalski's modification. The aircraft had compiled an impressive combat record. In Europe alone, P-47 seconds were credited with 3,552 air-to-air victories, destroyed more than 7,000 locomotives and nearly 9,000 tanks and armoured vehicles in ground attack missions, and flew more than 546,000 combat sorties. Those numbers represent more than statistical achievement. Each sortie represented pilots who returned safely, missions completed successfully, and enemies who couldn't inflict damage because American fighters controlled the sky. The wastegate modification's contribution to that success is impossible to quantify precisely, but it was real and significant. Every pilot who climbed faster to intercept position, every engagement won because of energy advantage, every bomber formation protected because escorts arrived on time, all of these owed something to one mechanic's decision to trust his instincts over the technical manual. Technical Sergeant Frank Kowalski died in 1994 at age 80. His obituary in the local Pennsylvania newspaper mentioned his military service, but didn't detail his contribution to P-47 performance. Most of the pilots whose lives his modification saved never knew his name. That anonymity is typical for enlisted maintainers whose work enables others' achievements. The visible heroes are the pilots who shoot down enemy aircraft and return with dramatic combat footage. The invisible heroes are the mechanics who ensure those pilots have aircraft that perform when lives depend on it. But history remembers, even when memories fade. The wastegate modification story survives in technical reports, after-action accounts, and oral histories from veterans who understood what changed and why. It survives in the design of modern aircraft engines that prioritize responsive control systems. It survives in maintenance doctrine that values field experience and enables rapid innovation. Most importantly, it survives in the principle that good engineering serves operational needs rather than defending theoretical purity. The P-47 wastegate modification wasn't the largest or most dramatic innovation of World War II. It didn't change the war's outcome the way radar or atomic weapons did, but it exemplifies how wars are actually won, not through single decisive moments, but through thousands of small improvements that compound into overwhelming advantage. Better climb rates, faster response, more aggressive tactics enabled by confidence in equipment. These incremental gains, multiplied across hundreds of aircraft and thousands of missions, determined who controlled the skies over Europe. Alexander Kartveli designed the P-47. Pratt & Whitney built the engine. General Electric created the turbo supercharger. All of that brilliant engineering provided the foundation. But Frank Kowalski made it work. He closed the gap between what the aircraft could do theoretically and what pilots needed it to do actually. That's the difference between engineering and maintenance, between design and operation, between building capable machines and unleashing their full potential. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.